Hello folks, this is Todd Coburn of Cal Poly Pomona with Lecture 1 of Aero 3261's Structures 1. Today we're going to cover force, deflection, stress, and strain. And we're going to learn to evaluate these stresses. This is going to be one of the critical lessons that everything else will build on. Before we get started, it's good to go back and review what we've learned from statics. For example, how do we show forces? This first figure shows that we have a force on a member. We could call this an axial force. We could call this force is going to cause a normal stress. We're going to learn about that in a minute. So whenever we see an arrow, a vector, that's how we show forces with vectors. We often show moments with vectors. We're used to seeing moments with little curly vectors, like I'll show you in a moment, but also when we see a double-headed vector, this typically indicates that it's a moment, and that's showing the axis. Using the right-hand rule, you jam the thumb down the direction of the arrows, and your right hand, the fingers will wrap in the direction of that moment. You can picture, a lot of times we show a little moment like this, that means this is a moment in this direction, and it's acting on the structure like this. Compression up here and tension. Picture your palm pulling away from the section and your fingers pressing into it, causing tension and compression. We'll learn about bending moments later, but you ought to, at this point, understand how they look when you encounter them. Therefore, this little figure here shows a torque. Torque is just a moment, but it's a special kind of moment because it's a moment that causes torsion on the material. And then if we see this is the way we often see them in statics as well. What you can see there is if you look, jam your thumb in the direction of the moment, which would be coming toward my face, our fingers are wrapping on the right hand side, and then on the reaction, action, reaction pairs on the left hand side. There's our reaction, here's our applied force, or a moment. Got that? This is important to understand. This is just laying the groundwork for where we're headed. Okay, so let's just take a look here. A lot of times what we'll do with structures, there are some things we can measure in engineering and some things we can't. This is a typical test machine. You'll see this in our Aero 3570L lab. And a lot of times we use a sample like this where we're pulling on the sample to pull tension. And as we pull, we're measuring the force that we applied, and we're measuring the deflection of the member. Now, since the member often has a change of cross-section, it has changes in the way that stress is distributed based on how we hold it. We'll often neck that down to a nice uniform section, as you see in this sample, and apply a couple gauge marks that will then measure the length, the original length between the gauge marks and the change in lengths. This is actually getting a little ahead of ourselves, but that's the kind of idea and how we can evaluate the effects of forces on structures. Now, if we did load that, and if we plotted the amount of force that we apply on the horizontal axis, and then the measured deflection on the vertical axis, we're going to find that the deflection changes in a proportional manner with the force. Up until a certain point, we'll see that force-deflection curve goes nonlinear. We call that point the proportional limit. That's the point where our stresses go from elastic, where we can get everything back, to nonlinear and inelastic behavior. We're going to learn more about this as we go. Now, often, if we do this, we will flip those two. We'll plot the deflection on the horizontal axis and the force on the vertical axis. And we get a curve like this, where we can see the proportional limit, where our load-deflection curve goes from linear elastic. Linear meaning it's a perfectly straight line. Elastic meaning anything that happens if we let off the force, it will return back to the original state. After that, not only does our force-deflection curve go nonlinear, where it's no longer linear, but also we will now get permanent deformation in the material. We'll learn a little bit about that as we go. We're going to often see that force increase more and more, and yet now we're getting proportionally more deflection as we pull on this until we finally break. And before we break, many of the materials we're going to see will actually see a reduction in force with an increase in deflection. What that means is the material is moving so quickly that you actually can reduce the force and continue to pull deflection. I can't think of a really good example right now, but there are many places in reality where we'll see that, where we're pulling and all of a sudden it gets really easy to pull. It's like it got easier to pull and you see a drastic notice because we went into the plastic range. We also could do the exact same thing with a moment. If we apply a moment to a structure and measure the angle of twist, we get a similar curve as you see here. Now, if we take our load deflection curve and plot various materials, we will see that different materials have different load deflection curves. The material affects the load deflection relationship, and so does the cross-sectional area. A member with a larger cross-sectional area will take a lot more force to cause the same amount of deflection. And so while load deflection curves are useful, we find that actually we can characterize our materials better if we tweak what we're plotting a little bit, if we normalize these to two values. Since the load deflection curve, the relationship that we see here is a function of the force, but that effect on the structure is also a function of the area, we will normalize the load to the area, which means we're going to take that load, P, the force, if we call it P, and divide it by the area of the cross section, A, then that is what we're going to define as the stress. We're going to look at a formal definition of stress in a minute, but basically force divided by area is stress in the most basic form. What that means is we could call that, since it's the force per unit area, we could call it a force intensity. I haven't ever heard anybody call it that, but we could, because that's really what it is. So if we divide the force by the area. Now the deflection, what we find is if you pull on these members for the same force, a member that is shorter will deflect less under that force than a member that's longer will deflect. So it's not only, the deflection is a proportion to both the force and the original length of the member. So we're going to normalize the deflection by the original length of the member. So we're going to normalize the force against the area, P over A, which is what we're going to call stress. And we're going to normalize the deflection with the original length, and we're going to define that as strain. We'll see a formal definition in a minute. Now, if we do that, we're going to get a new plot that looks kind of like this. So we've normalized our force to the area, that's called stress. We use the symbol sigma often, or lowercase f in aerospace. And strain, usually we use epsilon for that, is just the deflection divided by the original length. Now if we plot this load deflection curve in this manner, this is called a stress strain curve, and we get a family of curves like this. Now you might not be impressed, but what this means is if we have, say, a soft aluminum, and if we make a bunch of parts of the same rough dimensions, but different areas perhaps, then they will all exhibit the exact same curve as this lower curve. If we have a low carbon steel and we make a number of parts out of that low carbon steel, they will all see basically the same stress strain curve as what you see for low carbon steel. If we have a high carbon steel and make a bunch of samples out of that exact same material, even different sizes and lengths and everything else, they will have the same stress strain relationship. So now, by doing this normalization of the force to the area and the deflection to the original length, which is giving us stress and strain, we find a curve that's much more useful in characterizing how that material behaves under loading. And this is important because when we can understand how a material should behave in different forms, it allows us to engineer a lot of different structures and use what we already know without being surprised with unwanted or expected failures. So our force in the first one is just force is equal to the spring constant times deflection or some relationship, and our stress is related to our strain through some other constant. We're going to call that the modulus. We're going to introduce the modulus in a bit, but this is how the modulus is defined, and this is going to introduce us to Hooke's law, which we'll be looking at shortly as well. So if we define our stress, our stress, we said we could call it a force intensity. It's just the force divided by the area. So if we have a square rod as we see here, what we're going to look at is what is the area that this applies to. Since if you take a cross-sectional cut, any cross-sectional cut that's perpendicular to the force will define a different area, and since this is all constant section, it's the same area. So if we take that force and divide by that area, that's the average force in the section as we see in this section cut here. Now we're going to find out that the stress just doesn't magically distribute itself evenly. It's like having a group of 5 friends that all are hugging each other, and you grab onto the arm of one of them, yank on him. The force on that person is pretty direct. The force on the others is a function of where they're distributed. In the same way, since structures are people too, if you pull on a member, a structural member, the force doesn't magically even itself out throughout the section. It takes space and distance in order to do that. And that gets to a more complicated type of analysis. So a lot of times we're just going to pretend that when we see a force on a structure, we're going to pretend that it's average. We're going to look at the average stress. We'll learn when we can't do that and we can do that, but a lot of times we're just going to do that simple approximation. P over A is the average stress. We can use sigma as the symbol to define stress. That's how a lot of the introductory texts are in engineering, especially in mechanical and civil engineering. And in aerospace, though, it's very common to use the lowercase f as our symbol for a calculated stress. And if we've got a tension stress, as this one is, we'll a lot of times put a little subscript T. So our units are just pounds per square inch, or PSI. If we have 1,000 pounds per square inch, some people call it a KPSI, but it's very common just to call it KSI, which is kips, or 1,000 pounds per square inch. So a basic procedure to calculate stresses on a part is to figure out what forces are on the member, look at what the cross-section is that force acts on, take the minimum cross-sectional cut and calculate what that area is, and then compute the P over A stress. Once you have the stress, the question is it good or is it not good? And now you need to understand what the allowables of the part are. So what you're going to do is go find, well, how much stress does this particular material, is it good for? And then we will evaluate it. We can use either the factor of safety or the margin of safety. The factor of safety is just the allowable stress divided by the calculated stress. By this definition, this is acceptable if your factor of safety is 1 or more. If your factor of safety is 1, then the structure can hold that stress without failure. And if it's greater than 1, it can hold more than that stress without failure. If your factor of safety is less than 1, then the structure fails under the loading. Factor of safety is used commonly in civil and mechanical engineering. In aerospace, we typically bury the factors of safety in the loads. There are requirements for what the factor of safety is in aerospace. Usually it's 1.5 for most aircraft, helicopters, and those kind of analyses. So we'll take the max loads we'd ever see, we call those the limit loads, we multiply them by the prescribed factor of safety, which is generally 1.5. That gives us a new set of loads, and we generally analyze to those. Since the factor of safety is already buried in the loads for much of the aerospace analysis we're going to do, we don't use factor of safety to evaluate the design. We use what's called the margin of safety. The margin of safety is defined as that allowable divided by the calculated stress minus 1. If the margin of safety is 0, then that means the structure will hold the load successfully. If it's a negative margin, which means that is smaller than 0, then the structure fails. And if it's larger than 0, it means you have ample room for additional load. Make sense? It's critical to understand this. We're going to be using margins of safety to evaluate our stresses from here on out. We're going to be calculating stresses. We're going to be figuring out what the allowables are, and then we're going to be evaluating the margin of safety to determine whether or not the structure is expected to fail or to survive. Now, stresses, even though we did a simple P over A kind of check, we know that stresses are force intensities, and that it doesn't just magically get uniformly distributed throughout the structure. For example, if you pinch a piece of your arm and pull on it, you're going to find it hurts. and it hurts more, and you get more deflection right there in the vicinity of the load, and out away from the load you don't feel it at all. Structures are people too, and they do the same thing. If you really want to know what the distribution is, we could use calculus. We could define it, the stress is just the change in force with respect to the change in area, or the little increment of force on every increment of area as the limit of that little area gets smaller and smaller and smaller. This tells us what the exact force is on a tiny little element, and if you took the average of all those little elements across the cross-section, you will match what the average stress was using P over A. Now there are times when we use this calculus to calculate the stress, and there are times, or most of the time, where we're just going to take P over A. What we will do is go back to the calculus as we look at different kinds of loadings and what effects they have to the structure. But we're often going to come up with a simple equation like P over A to figure out what the stress is. Since the stress is defined in this manner, we can calculate the force by just taking the integral of the stress with respect to A. Okay? All right, let's go ahead and take a moment to introduce tensor notation for normal stresses. Now, this is kind of an advanced topic, but we're going to run into this a few times. We're going to need to understand it a few times, and in order to understand it later, it's better to just introduce it now. Now, force we know has magnitude and direction. Stress is thought of as just a magnitude. However, the stress is based on a force which has magnitude and direction, and an area, which actually could also be thought of as having magnitude and direction. An area definitely has a magnitude, and when you think of the direction of the area as the unit normal, or the normal to the area, then you can recognize, oh, the area is a vector, can be defined as a vector, and so can the force, and therefore we're going to need basically two vector indices to identify what kind of stress it is. For example, on this little element, we see we got an x, y, and z face. The x face is b by h wide. That's the magnitude of the area. And we have some force applied to that. You can see by the little red vector. The stress is acting on the area. Now, if you look at that area BH, the x-axis is perpendicular to that area. So the unit normal for that area is x. Now, since our stress now needs an area and it needs a vector, a force defined, the stress is acting on the x face in the x direction, therefore we use subscript xx. Got that? So a tensor basically is going to have a stress and it's going to have two subscripts. We're going to have the first subscript represents the direction of the unit normal of the area. The second subscript defines what the direction of the force is. So if we see, we just said those things. If we see this guy here, we see that the stress here is acting on the y area, the area that's normal, perpendicular to the y axis, and the force is acting in the same direction. Since both of these, this sigma xx and sigma yy, the force acts perpendicular to the area, these are called normal stresses. If it's a long member and the force is acting along the member, either in tension compression, it's called an axial stress. These are also called normal stresses because the forces are perpendicular to the area. If we then look at the face AH, we see that the stress on that face is on the z area in the z direction. ZZ. Got that? That's a little introduction to tensor notation. We will build on this as we get into other kinds of stresses, and then later when we're doing three-dimensional stresses for a couple simple ideas, you will be able to understand what this tensor notation means. All right, so let's go back to the strain. So we introduced the strain as just the normalization of the deflection to the original length. So if we have a member like this member BC and we pull on it with a force, that member will get longer. It had a length, an original length, and it gets longer. We could call that the deflection. The stress is just P over A. That's the average stress. And we said the strain is just the deflection over the original length, the delta L over L, or the delta over L. That's the strain. That's how we're going to define strain. Now, since strain has units of length over length, some people will say it's dimensionless, but actually I think it's better terminology to say that it has units of inches per inch, because we're saying it has a deflection and it has a length. So the strain is in units of inches per inch, okay? So we could express it as delta L over L or as delta over L, and once again we can get it from our little tension sample here. So we define stress, generally using the average, but we understand we can look at the detailed stress distribution, and we got the idea of strain, deflection over original length. These are foundational, critical concepts that we're going to use over and over again in this class. Take a moment, make sure you understand these. Also, when you get to the homework, make sure you do enough homework problems to understand these fully. All right, so we talked about the load deflection curve, and we transitioned that to the stress strain curve. This is a couple stress strain curves that we will encounter. In the first one, we see that we have a linear range. It's actually a very short deflection range. And then we have this weird original curve where we see that the stress comes up to a certain value, it drops a bit, and then it climbs up to a higher value and then drops again. This kind of curve, materials with a definite yield point like steels, many steels exhibit this kind of behavior. Now, depending on the steel, it will go to either a higher or a lower stress, but this is a common shape for steels. The lower one, you'll notice, doesn't have a defined yield point. Oh, with the steel sample, or when you have a definite yield point, we're going to call the yield stress that first peak, and the ultimate strength the max value you find. Okay? If we have a material that doesn't have a definite yield point, like the lower material, it has no definite first peak, it just has a single peak, and that's the ultimate stress. We're going to use a different method to find the yield. We're just going to come up with an arbitrary definition of yield. What we're going to do is take the slope of that curve initially, the stress-strain relationship, that slope of that, stress over strain, of the initial part of the curve, and we're going to slide it over till it goes through the 0.002 inches per inch strain. That's called 0.2% strain, right? Because 2% would be 0.02, 0.2% is 0.002. That's a common mistake made by students, by the way. So we're going to take that initial slope of the original stress-strain curve, and then we're going to slide it over through the 0.002 inches per inch strain, and wherever that new curve strikes the original stress-strain curve, we're going to call that point the yield stress. Okay? That seems kind of arbitrary, but actually there are reasons that we'll discuss as we're going forward of why that is valid and reasonably accurate, and it keeps things simple. Got it? Okay, so let's take a look. This is a stress-strain curve. Now you'll notice on the other stress-strain curves we only saw the tension behavior. We're applying tension. That's that upper right quadrant, the first quadrant here, is the kind of stress-strain curve we see going from 0 up to some stress, some positive stress. However, if we had applied compression to the material, we would have had a negative deflection for most materials. And so we could call the full range stress-strain curve something like this. The full range stress-strain curve is the one that goes both in tension and in compression. It looks like this. Does that make sense? So often in elementary text, we'll just see this first quadrant, all the positive values, and the reason they don't show the negative values is because it's often pretended that they're the same. And it's okay to pretend that, because most of the materials that we're going to use in engineering, the most standard materials, the steels and the aluminums and magnesiums and things, these all have stress-strain curves which are nearly symmetric. They're almost symmetric, which means the stress-strain behavior in compression is nearly the same as it is in tension. Now, it's not completely the same, as we will find out as we move forward. So if we see a stress-strain curve that's full range, meaning it shows the tension and compression behavior, we will use the entire curve to evaluate our material. If we see only a first quadrant stress-strain curve, we will just guess that that material is symmetric enough and pretend that the compression behavior is identical to the tension behavior. Does that make sense? So let's look at some points. We know that the slope of this initial curve is That's the modulus, actually. Stress divided by strain. If you look at the slope of that curve, that's what we're going to find is the modulus E, the modulus of elasticity E. Remember, we saw force equals spring constant times deflection, and we saw stress equals modulus times strain, where modulus is just the slope of the curve. If you take the slope of the linear part of the curve, that's the modulus of elasticity, and that's the first thing we need to know. The next thing is the yield point. Now, if we want the yield point, we're going to take that slope, that's defined by that blue dashed line, slide it over through 0.2% strain. Wherever it hits the curve is the yield. We can have a yield allowable. I've got a capital F. Oh, so that's another thing. I told you we used sigma often for calculated stresses and lowercase f for calculated stresses. In aerospace, we also use a capital F to represent an allowable stress. So if you see a capital F, it's often not a force, but an allowable stress. And then we use subscripts to talk about what kind of stress. So you'll see FTY is the allowable stress. It's the yield stress in tension. Allowable stress, tension, yield. You see that? FTU is the allowable stress in tension, and it's the ultimate one, the most it can go to. Ultimate is a word that we use to talk about the very most. So the uppermost point of the curve defines the allowable of the material, the ultimate tension allowable FTU. If you look at the compression side, you see the ultimate compression allowable is FCU. F meaning capital allowable stress, C meaning compression, U meaning ultimate. We see the ultimate strain, the most tension strain we can go to, is the furthest most point that's shown on the curve. In this particular case, it looks like about 0.046 is the ultimate strain. We call it strain epsilon, T for tension, and U for ultimate. So we can see the allowable ultimate tension strength, FTU, the ultimate tension strain, epsilon TU, the allowable yield strength and tension, FTY, the modulus, which is not written on here, which is the slope of the initial curve, E for tension. We don't normally put a subscript on that. We can see E for compression. Usually if we're talking about the modulus for compression, we'll use E subscript C. So we see this slope here of this curve is E. It is the change in stress divided by the change in strain, which in this particular case, if we pick a point, say here, we'd say that's 4 KSI divided by, what's the strain? Looks like about 0.002, 0.004, 0.004. See that? And that is your modulus. The slope in compression, E sub C, is going to be, let's just take 10 KSI, and we got about 0.01. Looks like it's about the same value as it was for tension. Well, this is, right? Makes sense? This is our FTU, our ultimate tension allowable. This is our ultimate strain allowable, ETU, for tension. When we take this slope and slide it over through 0.2% strain, we find it hits here. That's our yield tensile allowable. The place where the curve goes from linear to nonlinear behavior, that's called the proportional limit. We could call it the allowable tension proportion. Now, we're not going to use this for hardly anything in aerospace, but you should understand what that is. Mechanicals use the proportional limit a little more than we do. We see the same things, the FCU ultimate, which is right here. We see the ultimate strain, which is whatever this value is. We see the yield by taking this slope and sliding it through here and then reading what that value is. And we can see where that goes from nonlinear to linear behavior, which is our proportional limit. You need to understand all those and be able to identify those points on the curve. Every engineer should be able to do that. Got it? So our stress strain curve has a wealth of information, right? FTU, the maximum stress that the material can withstand. That's an allowable. Yes, it's an overstrain in the linear portion of the curve. You'll notice we could talk about the modulus other places. Let's do that for a minute. we said that the modulus E is just this slope here, right? But actually at this stress up here, we've got a different modulus, and at this stress here, we got a different modulus. That's called the tangent modulus, which is given a subscript T, not because it's tension, but because it's tangent to the curve. You could also talk about the tangent modulus for compression, okay? We're not going to use that, but we should be aware that the modulus is actually a function of the stress. Usually we're going to use the modulus elasticity from the elastic portion of the curve. That initial modulus is what we're going to use for most everything we do, but we need to understand that that's not strictly correct. That's an approximation, okay? Our ultimate strain is just you take the furthest most point shown on the stress strain curve and we read what the corresponding strength is. Our elongation, so this is a new term. The elongation is just the maximum strain written as a percentage. It's very important to understand this. So if you know what the maximum strain is, if your maximum strain is, let's just say our maximum strain for something, TU is say 0.09, that's like in lumen, inches per inch, then the elongation for that material in tension is just that written as a percent, so it's 9%. If our maximum strain were, let's say, let's say it's 0.15, like some aluminums, inches per inch, that's a lot of strain, then our elongation for that material is just 15%. That means that the part will elongate 15%. If you were to have an elongation of 20%, what that means is the part will get 20% longer before it fails. Very important to understand this. And we can do the exact same thing for compression. We just take the compressive ultimate strain and turn it into a percentage to get what the elongation is. The reason elongation is important for us is because there's sometimes we're going to need the ultimate maximum strain, and yet we don't have anywhere to find it. But we're going to find out in our appendix that the elongation is shown, and we can take the maximum ultimate strain as just the elongation. This ultimate strain here is shown as a maximum value, but we generally are saying that it's the ultimate strain. Also, you could call it the max strain or the ultimate strain, same thing. Got it? Proportion limit is where we deviate from linear to nonlinear behavior. The yield strength, we talked about how we define that by just shifting the original modulus slope through the 0.2% strain. This is a typical, looks like a steel because we have a definite yield point. And we talked about the full range versus the first quadrant stress strain curves. Full range is the one shown above where we see everything, both the tension and compression behavior. First quadrant, we're just looking at one of those quadrants. Got it? Now we can, once we understand stress strain curves and a little bit about how these materials look, we can quickly identify what kind of material we're testing if we know what the stress strain curve is. This material here has no definite yield point. That means it's probably aluminum or something like that, and the 50 KSI is a common allowable yield. 50, 60 KSI ultimate is common for aluminums. This has a definite yield point, but it's not really strong. Its FTU is only about 63 KSI, so this is probably a mild steel, right? Not a real strong steel, but is a steel. This one here has a really wacky looking curve. It looks backwards, like somebody deformed the thing. When we see behavior like this is probably a natural rubber or something similar to that. You'll notice that the tension strength of this material is very, very bad, but the compression strength is quite good. This looks like a concrete, about 5 KSI of compression strength and less than 1,000 PSI of tension strength. And this particular one, another material that has a really weak tension strength, about 20-ish KSI, but a very good compressive strength, is something like a cast iron. Okay. Next idea, so when we load up a curve, if we were to test it, we would be applying force and measuring deflection, and then we'd be calculating the stress and the strain. And if we plot the stress and the strain, we get a curve like this upper curve. However, it's important to know that if we load this thing one time, it's going to go, our material behavior is going to go right up the stress strain curve. But let's say we load up part way like is shown here, stop, and then unload. Now it doesn't go back down the stress strain curve. If we had done that down in the elastic range down in here, we would continue to go up and down the stress strain curve. As soon as we go past the proportional limit, we now have permanent deformation of the material. It's called residual stress as well. So if we come up, say, to this point here and then let go of the load, it will actually go unload along the same curve as our original slope. So if you look at the original E and you come down from there following the same slope, that's how the material behaves. Once you're completely unloaded, you now have whatever this value of strain is now a permanent strain in your material. It's permanently deformed. It's longer than it was. Now, if you load it up again, if you start loading after that, it's not going to go up the original curve. It's going to go straight back up this new curve and then start loading more. So you'll notice where before we had a nice soft relationship transitioning from the linear to nonlinear region, now you'll notice that it's a lot sharper. And if we load even further and unload and come back up, it gets even sharper. What that means is we've changed the material and we've actually moved the yield point. While this material that's loaded down in here didn't actually yield until we get past the proportional limit, you'll notice the yield of this new material, once we've loaded a little bit, has climbed from whatever it was up to this new value shown right there. So actually, if you load up a structure in the lower load realm, but above the proportional limit, you're going to end up taking your stress strain curve and you will change it until it gets a stress strain curve that looks a lot more pronounced, where that's your new FTY. So if we went to the original curve, we would take this slope, move it to the 0.2% offset, but under low loads, eventually that 0.2% offset will become the point where your yield is. So actually, even though we kind of winged it and came up with this 0.2% strain idea, it actually works pretty good, because if you load up your structure with any significant load, that will often become the yield after a while. Make sense? That's what all this says. Got that? So we're not going to do a lot with this, but I expect you to understand this concept at this point. Okay. So if we go back to energy, remember energy is just force times distance. Now if you take force, let's say we have a part, and let's say we pull on it in this direction. Force, if we measure the energy is just the force times the distance, right? That's the work. Force times distance. If we pull on it this way and it moves that much, that's called work, right? We have a force and it caused a deflection. Force times deflection is energy. Now, if you have a force applied in this direction and it moves in that direction, forms in that direction, that's called magic. We're not talking about that. This class is not about that. For energy, you have to have a force and the corresponding displacement in the same direction. Make sense? So this energy is just a summation of the force times the unit deflection. We could actually say this integral, right? Since it's the force per times deflection, then the area under the force deflection curve, here's our force deflection curve. Since our energy is just force times deflection, the area under that curve is the energy. If we have stress versus strain, the stress is just the force divided by the area, and the strain is just the length, the change in length divided by length. What that means is that's the work divided by the area and the length, which is volume. So actually it's the energy per unit volume. These are two important characteristics. We're going to only use energy a little bit this semester, and we're not going to do anything with that energy per unit volume until we get to failure modes. But as you go into higher concepts, you will come back to these terms to develop and derive more complicated ideas. That energy per unit volume is actually called the toughness, and we will look at that a little bit when we get into fracture mechanics. Okay? Got all that? Okay. So now we've talked about stresses, how to calculate basic normal stresses, and how to calculate margins of safety once we have the allowables. We've seen how to identify what the allowables of the material are from our stress strain curve, right? Our ultimate allowable is FTU and FCU, and our yield allowable is FTY and FCY. But where do we find these values if we don't have a stress strain curve? Well, we're going to go to the back of our book. MMPDS is the industry standard for this, and I've made tables that simulate that so you can get familiar with how this works. If you go back to the appendix of your handbook, you will find a bunch of different materials. And we're going to find a wealth of material properties in these tables. I'm going to show you how to do that in a moment. Okay? Okay, we already talked about margin of safety and factor of safety. A couple other terms are in order. Allowable is the max load or stress that a material can withstand. We're going to use that as a generic term. We could talk about the yield allowable, FTY, or the ultimate allowable, FTU, or FCU. Okay? Those are all allowables. Later we'll get into stability allowables. Those are allowables also. Our limit load is the max load we expect in service. Our ultimate load is the max load the limit load times whatever factor of safety is required for ultimate loads. Sometimes factors of safety are required for limit loads for yield analysis. Usually that factor of safety for limit load is just 1. So we'll evaluate the limit load against the FTY, the yield of the material. Ultimate loads we're going to evaluate against the ultimate allowables, and we'll take the limit load times a factor of safety. These are our factors of safety, but you know that we're going to actually bury our factors of safety in our loads, and we're going to use the margin of safety to assess structures. We said that before. Got it? There's a detailed section in your handbook on margin of safety. Make sure you read that and understand this. Okay, so take a look at your handbook, flip back to the appendix, and what we're going to do if we're trying to find allowables for material, first we're going to find out what kind of material it is. Is it aluminum? Is it a steel? Is it titanium? Right? Magnesium. I think I finally added some magnesium to our handbook. Then you're going to figure out what is the grade. So 70-75 is a typical grade. We also have the form. Is it sheet? Is it plate? Is it an extrusion? Is it a casting? You're going to need to identify that. So you're going to first pay attention to the header talking about what material it is. 70-75T sheet and plate is shown here. You'll notice this table is like two tables. Actually, the new version of the handbook has these two curves, these two tables split. But we have one for sheet and plate and one for when it's clad. So what we'll do sometimes is, because corrosion is so detrimental to metals, a lot of times what they will do is take one material that's strong and they'll put a little tiny thickness of some other material that has better corrosion resistant properties on the outside. That's called clad. Okay, we're not going to go deep into that, but you need to recognize, is your part clad or not clad, and find the allowables appropriately. Okay, so we're going to go, and let's say we have a 0.071 inch thick 70-75 T6 aluminum sheet, and we need to evaluate the tension strength. Well, if we have, first we're going to say, okay, we're looking for 70-75 aluminum. It looks like we got aluminum here, 70-75. Doesn't say anything about clad, so we're going to assume it's just sheet. Oh, another word of caution. This table, you'll notice there are things called sheet and things called plate. Basically, that's the same thing. As it gets thicker, it's generally called plate. There's sometimes I may say it's a plate or a sheet, and you'll say, oh, but there's only a sheet allowable or a plate allowable. Well, if it's got those listed separately, great, use the appropriate one. But if you can't tell the difference, just assume sheet and plate are the same thing. Okay? So let's say we have 071. We find that, okay, it looks like we're in this leftmost piece, 70-75. And then we go and look and say, okay, it's sheet, great. What is the thickness? 071. So we're going to say, all right, we've found that it's 70-75. We then are going to say T6. So it looks like that's over to the left. And then we're going to say, all right, for this thickness, 071, it falls in this first little set of columns. You'll notice for this thickness, 071 falls between 040 and 125. We have both A basis and B basis allowables. I've written up a little write-up on what those bases mean in your handbook in the appendix, at the start of the appendix. Make sure you read that and understand this. I expect you to understand it, but we're not going to do a lot with it other than to say that for our structures, we're going to use B basis allowables. In aerospace, you're supposed to use A basis allowables if you have a part that's the single point of failure. If that fails, the whole thing fails. If you have a redundant structure, then you use B basis. For example, I have 5 fingers. If we cut one off, that might not be happy. I still have 4 other fingers. That's redundant structure. I'd use a B basis allowable because it's not critical. But if we're talking about my neck, if my neck goes, my whole head is gone. That's a single load path failure, and therefore it would require an A basis allowable. You got that? Okay. Forget this about using Poisson's ratio 0.33. We haven't learned about Poisson's ratio yet, but you can see the Poisson's ratio is shown in here. We'll talk about that when we get to it. Basically, we're going to go and read this curve and find its B basis. Since we got a tension strength, we've got, you'll notice over here to the left, let me turn on my pen. You can see we have FTU, that's our ultimate allowable from our stress strain curve, right? If this is our stress strain curve, that's the point right up here. We've got FTY, that's the point right here. Now you'll notice there's no FCU, and since there's not, we will assume that FCU is just equal to FTU, right? Just a compression value. None of our tables have FCU. We will always assume that it's FTU, all right? But we do have an FCY. Now we're not going to be using FCY for some time now until we get to stability, but if we needed it, we can read FCY. That's right there. This is FTU, this is, FTY. Here's our FCY. We have an FSU. We haven't talked about shear yet. That's our shear allowable. We'll get to that later. Bearing, we haven't talked about that yet. We're going to learn about our bearing allowable pretty soon. This is our elongation, right? So if I ask you what's the maximum strain, you're going to say, well, for this material, I've got this, I've got this, I've got this. It's B basis. That's the elongation is 9%. That's the max strain. ETU is going to be 0.09. That max strain written as a number rather than as percent. Got that? This is our modulus right here, 10.3 million PSI. I call that MSI. And we see here that actually in compression we have a slightly different modulus. Most of the materials we're going to see will have a slightly greater modulus for compression than tension. It's 10.5 for compressive loads. You should be able to find the E. You should be able to find the E sub C. You should be able to find the FTU, the allowable, FTY, and the FCY at this point. Okay? And everything else we will get to later. All right, let's look at a couple ideas quickly. Let's say we have a part like this. We have this bar loaded in tension. What is the normal stress? Just P over A, right? Bang. Got that? Remember, kips is 1,000 pounds, 10,000 pounds, 0.1 inches squared. Great. Well, let's see. What was the stress on this part? Just P over A. What area is appropriate? The normal stress is going to be the stress on the area that's perpendicular. That means it's P over BH, right? What kind of stress is this? It's a normal stress, and it's tension. What is the stress on this part? Now it's just P over this other area, which is BA. You see that? What kind of stress is this? Once again, it's a tension stress. It's a normal stress. What's the stress on this? It's P over AH, except now it's compressive stress. See that? That's compression. Got it. Let's look at our stress strain curve. Let's say we want to know what's our ultimate tension strength. We're just going to go to the max point on the curve and grab that. That looks like it's about, what, 14.5 KSI. What's the proof strength? Okay, reword this a minute. What's the proportional limit? Proportional limit will be the point where the stress strain curve goes from linear to nonlinear. That's that point there, about 5 KSI. What's the modulus? Well, you take 5 KSI divided by the corresponding strain. Well, this looks like about 0.005, right? Which makes a modulus about 1 million, which is a really flimsy material. What's the tension yield strength? Well, you'll start with the slope of the original curve. Now watch this carefully on the curve. You're going to slide it over through 0.2% strain, and wherever it hits the curve, that's your FTY. Got it? How about the ultimate compressive strength? Lowest point on the curve. It's right there. Looks like minus 20 KSI, right? What's the compressive modulus? Once again, you're going to look at the stress strain curve in compression. Look for where it changes from linear to nonlinear and divide the number. It looks like minus 10 divided by minus 0.01. Compressive yield, you slide that over until it goes through 0.2% compressive strain and you read that value. What's the stress on this? On the part, if your force is 50 kips? Well, what you do is you calculate the area of this part. How many guys can calculate the area of a section? You should not have made it through statics without being able to do that, because we learned that in statics. Calculate the normal area, divide the force by the area, that's your stress. Got it? What if we have a different modulus? Is the stress any different? No, modulus doesn't even come into the equation. Same thing. Got it? Let's say we have a part like this. Now, for a problem like this, the important thing, before you can actually solve this, you need to systematically determine what the forces are in the member. So the best way to do that is right below this loading diagram. We can call this upper one the loading diagram. Just bring some vertical lines down and draw your part down here. We start off with 12 kilonewtons in the part and its tension. So from point A, we have 12.00 kilonewtons in the part. Okay? And it doesn't change. Then you hit this point. At that point, we have 18 kilonewtons. Look, we got two nines, right? 18. So that makes it 30 kilonewtons, right? So we come up to 30 kilonewtons. And it doesn't change from here to here. Then we have compression, which means it reduces it by 8 kilonewtons. So now we're down to what? About 22 kilonewtons. And nothing changed. And then we hit this one, and now we pull the last part out, and it goes back to 0. So this is our axial load diagram, right? And this is our loading diagram. Now, once you have drawn this curve, it's really easy. You can figure out the stress in this member, or this member, or this member. At this cut, we're going to have the area of this part with this force. Any cut between here and here, we'll see this area with this force. And any cut between here and here, we'll have this area with this force. See that? If we hadn't carefully, systematically figured out what the axial loads in the part were first, we would have probably gotten a wrong answer, even if we understood the rest of the procedure. And that looks like this. Okay? That's all we got. Make sure you understand this. Make sure you read all the sections in the text that are shown in the syllabus. Also, there's some preliminaries like chapter 1 and the appendices that we're dealing with. Make sure you understand the appendices of the appendix. And once you've done the homework, then go ahead and study how this works. Make sure you can do it. Make sense? Enjoy.